The conveyor speed is slowing down again.
Okay. All right, let me adjust the shaker settings.
Every industrial process begins long before motions start running. For onion powder, quality is determined at the farm. Soil mineral balance, irrigation timing, and climate directly control sulfur uptake in onions, an element responsible for both flavor intensity and shell stability once dehydrated. Onions store flavor compounds underground. Sulfur absorbed through the roots later transforms into volatile compounds when cells are broken. This chemistry is why onion variety and soil composition matter. Powder factories demand consistency at the molecular level. Mechanical harvesting is used not for speed alone but to minimize bruising. Damaged onion cells begin enzymatic reactions that degrade flavor before drying even starts. Precision harvesting protects chemical integrity. Not all onions dry the same way. Density affects moisture evaporation rates. Factories remove undersized or overly dense bulbs because uneven dehydration causes powder clumping and flavor loss later in the process. Despite automation, human judgment remains critical. Visual inspection catches early fungal growth invisible to sensors. Removing one compromised onion can prevent contamination across tons of powdered product. Washing is not cosmetic, it's chemical control. Soil bacteria can survive dehydration and later reactivate in moisture. High pressure washing reduces microbial load before heat processing begins. Before entering the factory, moisture content is measured. Too much water increases drying energy costs. Too little results in brittle powder. Every batch is digitally tracked to maintain flavor consistency across millions of servings. This is the last moment onions remain whole. From here, heat, airflow, and physics will transform a fragile vegetable into a stable, globally traded ingredient, onion powder. Once onions enter the factory, time becomes the enemy. Cutting activates enzymes that immediately begin altering flavor compounds. Industrial processing is designed to control chemistry, not just move product. Peeling removes the outer layers where microbial contamination is most likely. Instead of blades, factories use controlled abrasion and air pressure to avoid crushing cells and prematurely releasing sulfur enzymes. When onion cells are cut, enzymes called alinases mix with sulfur compounds. This reaction creates both flavor and harsh bitterness if left uncontrolled. Precision slicing limits exposure time before drying. Uniform thickness is critical. Even a 1 millimeter difference changes drying time. Uneven slices cause partial burning or moisture retention, both of which ruin powder quality. From slicing to drying, factories race against enzymatic degradation. Conveyor speed is engineered so onions reach heat chambers before chemical breakdown accelerates. Operators balance temperature and time. Too slow, enzymes destroy flavor. Too fast, surface scorching traps moisture inside. This control phase determines final taste intensity. At this point, onions are chemically unstable. Drying must begin immediately. The next stage uses heat and airflow to stop enzyme activity while preserving flavor molecules. This is where transformation truly begins. What happens next determines whether onion becomes powder or waste. Drying is not about removing water quickly, it's about removing water correctly. Onion powder quality depends on how moisture migrates from the center of each slice to the surface without cooking it. Water inside onions exists in free and bound states. Free water evaporates first. Bound water requires controlled heat to break molecular attraction without collapsing cell structure. Dehydration happens in stages. Early zones use lower heat to prevent surface sealing. Later zones increase temperature to drive moisture from the core. This gradient prevents case hardening. Airflow speed matters as much as heat. Too slow, moisture stagnates. Too fast, slices cool before evaporation completes. Engineers tune airflow to balance heat transfer and evaporation. Surface dryness means nothing if the center retains moisture. Testing ensures internal water content falls below microbial survival thresholds essential for shelf stability. Large factories recycle heat to reduce energy demand. Recovering thermal energy lowers costs while maintaining precise drying profiles, an invisible but critical efficiency layer. At this stage, water content has dropped by nearly 90%. Enzymes are inactive. Microbes cannot grow. The onion is now chemically stable. Drying preserves the onion. Grinding will define its form. Next, solid structure becomes powder. Grinding seems simple, but in food manufacturing, particle size controls everything. Flavor release, solubility, and flow behavior all depend on how finely onion is milled. Material enters the mill at a controlled rate. Overfeeding creates heat. Excess heat destroys volatile sulfur compounds, flattening flavor before the powder is even formed. Hammer mills break onion through impact, not crushing. Impact fractures cells cleanly, preserving aromatic compounds while achieving rapid size reduction. Roller mills refine what impact mills begin. Adjustable spacing allows engineers to tune powder coarseness depending on end use, from soups to seasoning blends. Laser diffraction measures particle distribution. Too fine, powder cakes. Too coarse, flavor release becomes uneven. Target size ranges are tightly controlled. Air classifiers use physics instead of screens. Lighter particles rise, heavier ones fall, allowing continuous separation without heat or friction. Flow behavior predicts how powder will behave during packaging. Pore flow causes inconsistent fills and weight errors across millions of units. Now reduced to powder, onion becomes modular. In the next stage, consistency and flavor balance are perfected. No two onion harvests taste exactly the same. Climate, soil, and season change flavor strength. Blending exists to erase variability and deliver consistency. Every silo is sampled, flavor